There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercurium, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendeleevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium.
Hey guys, hope everybody's doing okay. Welcome to Unit 8, which is on periodic trends. This unit is really interesting because we finally get to take a more in-depth and detailed look at the periodic table, the locations of the periodic table, and what do the locations of the periodic table tell us about the elements that are located there. So some of the questions I'll often get in class sometimes fall along the lines of, will element X react with element Y? Or what does element X look like? And as soon as I get asked those questions from students, I look at the periodic table and I find those elements that they were asking me about. Once I find those elements, since I know the locations of the periodic table and what some of those locations mean, I could predict some of the physical properties, some of the chemical properties of those elements, and I can answer those questions. So by the end of this unit, hopefully you guys can do the same, and we'll look at some of those more detailed properties as the unit progresses. Today we're going to focus on a quick introductory lesson on the periodic table, a little bit of the history of the periodic table, who's responsible for arranging it the way it is arranged today. There's a really interesting story to go with that. And what are the different locations of the periodic table and some basic properties that those locations represent. So what are some of the properties that we could predict based off of where the elements are located on the periodic table? We'll start with looking at how the periodic table was arranged and how it kind of morphed into what we see today. So what scientists did was they took the elements and they arranged them from lightest to heaviest. So they arranged them in order of lowest to highest atomic mass. You can see I just made up some blocks on the screen for you guys to take a look at. The numbers in those boxes represent the atomic mass. I just arranged them from lightest to heaviest. Now what scientists noticed was that there's a pattern, a repeating pattern of properties. So I color-coded the blocks. Those different colors of the blocks represent different properties that the elements have. So they had this big row of elements, right? And repeating properties happened every so often. So you can see that the color pattern repeats twice on the screen. So instead of having that big row of elements, what scientists did was they took chunks of the elements that repeated, like the pattern that repeated, and they just moved them underneath to make a block instead of a big row. Okay, so what did that create then? That created a table where elements with similar properties were organized in the same area or together. So I have an animation on the screen that I'm going to show you here. So you can see the repeating pattern of colors. What scientists did was they just took a chunk that repeated and moved it underneath like this. Okay, so I know that was amazing. We want to see it one more time. So you can see the repeating pattern here. What they did was they took a chunk, moved it underneath. They kept doing that, and now we have the periodic table in basically the organization that we have today. All right. One thing to point out, though, the modern periodic table today is not arranged based off of atomic mass. It might look that way, and I had this conversation with some students already in previous units when we got off topic. But there are 2 or 3 locations on the periodic table where you see a heavier element come before a lighter element. There's only 2 or 3 locations, so if you want to go on a little scavenger hunt and find those, see if you can figure out where they are. So what we have today is a periodic table based off of atomic number. The atomic number, if you remember from the previous unit, is the number of protons in the nucleus. So it kind of does follow the atomic mass, lightest to heaviest pattern, but there are a couple locations where there are exceptions to that. So we say the modern periodic table is arranged by atomic number, not atomic mass. Just something to point out to you guys there so you understand that. Okay, who's in charge of all this? Who can we blame for this whole periodic table that we have? Here he is. Russian scientist named Dimitri Mendeleev. He's the founder of the modern-day periodic table, published his first copy in 1869, so not all that long ago in terms of history here. But how did he do it? He spent many hours rearranging cards that had the elements on them and the element properties, similar to what I had on the previous slide. So he had all these cards, all these properties of the elements on them, and he tried to arrange them as best he could based off of properties. So I have a short clip here to give us the history of Mendeleev and some of his backstory. It's a really interesting story. That's why I'm showing it to you guys. It's part of one of the crash course chemistry videos that are out there. So maybe you've seen some of these other ones in the past as you kind of search through YouTube looking at random things. But it's a good story of perseverance, and you guys know me, my favorite word of all time is perseverance. So it's another good reason to show this clip. I think you'll find it interesting. As I'm recording this right now, and I'm looking at the picture of Mendeleev, a lot of people laugh when they see that picture of him. I'm coming to the realization that once this whole social distancing, coronavirus pandemic thing is over, that is probably what a lot of people, and myself included, that's what we're going to look like, okay? Because I don't know if you can tell in the little webcam view you have of me, but I need a haircut, and I'm not going to be able to get one for quite some time. So it's just a matter of time before I start to look just like Mendeleev here, and his unique and interesting hairstyle, okay? So anyway, let's take a look at the short clip here that I have for you guys. We'll review it, and then I'll show you one final short part of this.
Imagine you're in Siberia, and you're a 13-year-old boy, and your father, who was a professor but had gone blind, leaving your family of more than 10 brothers and sisters destitute, has just died. I know, downer. Your mom, to support the family, has reopened an abandoned glass-making factory in the small town where you live, largely because she wants to make enough money to send you to school someday. A year passes, the factory burns down. But your mom, she sees your potential. She knows that you have a keen scientific mind and will not see that squandered. So, with your siblings out of the house and on their own, she packs up your belongings, straps them to a horse, and with you in tow, rides 1,200 miles through the Ural Mountains on horseback to a university in Moscow. There, on your behalf, she pleads earnestly and effectively, and they reject you. So together, you ride another 400 miles to St. Petersburg, to the school where your father graduated as a scientist, and as luck, or extreme, insane, undeniably Russian persistence would have it, they accept you, and your saddle-worn butt, as a pupil. Your mother, having completed her mission, promptly dies. If you're doing your imagining as I've told you, you might feel a tremendous debt to your mother and a very deep desire to ensure that you achieve something on par with the sacrifices she made for you. And maybe that's one reason why Dimitri Ivanovich Mendeleev became the crown jewel of Russian science and a theorist who revolutionized how we see the world. Mendeleev spent a great deal of time in laboratories as a student, studying the burgeoning new field of chemistry. He worked with all the elements that you could work with at the time, and his knowledge gave him unique insights into their properties. Those insights would come in handy. Let's all imagine we're Mendeleev again. I like doing that. And that we know a bunch of stuff about chemistry, which, you don't yet. But we're imagining. So it's the 1860s, and about 60 elements are known to mankind, and their atomic weights are mostly known as well. So the simplest thing was just to sort them in order of their atomic weights. But interestingly, you, because you're clever pants, realized that the most significant relationships seem to have nothing to do with the atomic weight. Lithium, sodium, potassium, and rubidium were all extremely prone to reacting with chlorine, fluorine, iodine, and bromine. Beryllium, magnesium, calcium, and strontium were all similar but less reactive. But with a quick inspection, you, and to be fair, a number of other chemists, realized that there was a relationship between atomic weights, but it's periodic. At the beginning of the list of elements, characteristics repeat every 7 elements. On a side here, we now know that it's every 8 elements, but in the 1860s, elements were studied based on their reactivity, so the non-reactive noble gases had not yet been discovered, so the period occurred every 7 elements. As the mass of the elements increases, the repetition starts to look a little less periodic, though it's certainly still there, it just isn't perfect. Some of your colleagues, they're saying, well, such is life. It was perfect repetition early on, but later in the list it gets a little fuzzier. But not you. You become obsessed. Obsessed with the perfection of the periodicity. You write out the names and weights and properties of elements on cards, you lay them across your desk, shuffle them, tear them to pieces in frustration until one day you realize that you're simply missing cards. The numbers aren't working, not because there's something wrong with your ideas, but because some elements simply haven't been discovered yet. Armed with this insight, you insert gaps into the table, and things suddenly fall perfectly into place. 7 element periods for the first 2 rows with hydrogen in its own category, 18 element periods for the next 2 rows. You're so certain that you predict the properties of these missing elements, and when a French scientist comes along and says that he has in fact discovered one of them, you argue with him, saying that you discovered it first in your mind. And when you see his data, and it doesn't match yours, you publish a paper saying his data for the new element he discovered is wrong. That's how certain you are of yourself and this beautiful new theoretical framework you've created. And you know what the really crazy thing is? You're right! That French guy's data was wrong! You, never having examined the element he discovered, knew more about it than he did. Because you are Mendeleev, master of the elements.
Alright guys, to summarize some of the information from the clip you just saw, elements in the same column have similar properties. We kind of saw that in the animation I showed you before the video clip, but another name for column, we don't usually call the columns on the periodic table columns. We actually call them groups or families. Okay, so you'll probably hear me use those 2 terms instead of column. I'll use group or family, but know that that represents elements in the same column on the periodic table. Elements in the same column or group have similar properties, and there's a demo that I'll do, or a video I'll show you at some point in time of lithium, sodium, and potassium in group 1. I'll probably show you that when we talk about the trend in reactivity, but all 3 of those elements have very similar chemical and physical properties, and I'll save that for a later point in time. Okay, but other elements follow the same type of pattern in their respective columns. Okay, something else Mendeleev, well, not Mendeleev, but something else that we realized after a while was that each column has the same number of valence electrons. Now, we haven't really defined what a valence electron is. We'll formally define that a little bit later, but they are super, super important in terms of chemical and physical properties of an element and what they react with, what they bond with. So a quick definition of a valence electron, if you want to know. A valence electron is an electron in the outermost level of an atom. Okay, so we looked at the Bohr model at the end of last unit. We said that there's different levels that electrons are found in. So if you have an element with 4 levels of electrons, the electrons in levels 1, 2, and 3 are not valence electrons. Okay, they are inner shell electrons, and then the ones in level 4, if you have 4 levels in your atom, the ones in level 4 are valence electrons. Really important. It's the valence electron arrangement that determines the properties, both physical and chemical, of an element. So keep that in mind for future lessons that we do. All right, this is Mendeleev's original periodic table. I just think this is so neat. I don't know if anybody else is in agreement with me, but Mendeleev left blank spaces where no elements matched properties. So not all the elements were discovered, obviously, when Mendeleev was making his table. So he left blank spaces where there wasn't an element to put there. I just think this is so neat because he basically discovered undiscovered elements, right? Like, he knew there was an element in a certain location, like, you know, these blanks on here. He knew elements should go there. He knew everything about them, but he did not know what they actually were, right? So he said, like, basically, someday these elements are going to be discovered. It's going to look like this. It's going to react like this. It'll have properties like this. I just think that's so neat that he basically predicted future elements and said somebody someday will discover these, and I already know everything about it. And you kind of got a little bit of that from the clip that you guys watched. I just think that's so interesting and so neat that he was able to do that. And that's you know, based off of how much hard work he put into his arrangement of those elements and those cards into forming his periodic table. So I think that's pretty cool. Some other periodic tables that people have come up with follow the same general pattern of elements, but I just think they're interesting to show students because we could be using something like this if Mendeleev's table didn't work out. So we have a Dutch periodic table here, which I find really interesting. There's a scientist called Stowe. His periodic table is here. And my favorite one is this one, Benfey's periodic table. Looks like a seashell of some sort. You can still see hydrogen's in the middle here, and it spirals. Okay, and you still have, like, all the groups still match up. just a different kind of arrangement, which I think is pretty cool. Okay, modern periodic table, 7 horizontal rows, they're called periods. Here we go with our formal definitions. 18 vertical columns called groups or families. So if I say we are in period 5, that would be the 5th row down, so we'd be here. Right now the periodic table looks really nice because we have 118 elements. Everything is perfectly filled in nicely. As soon as they discover element 119 or anything after that, they're actually going to have to add a row to the periodic table, which will bother me with my OCD that I have. It'll add an eighth period, an 8th row, and that won't be complete, obviously, when they discover it, and that's going to bother me. So we'll wait till that time actually comes. And I already said this, it's arranged based off of atomic number. So that's really, really important to know. It's not based off of atomic mass, because there are some exceptions. It is based off of atomic number, the number of protons in the nucleus. Okay, the next couple minutes here, you guys are going to watch the second part of that clip that I showed you earlier, and it's going to match up with the next page in your packet. The next page in your packet has a blank periodic table, and you can just use your pen or pencil if you want to. Some people like to use colored pencils or markers to label the different parts of the periodic table. Just label the different parts of the periodic table. You need to know the main names of some of the components, like noble gases and transition metals, which you'll write down in a minute. So if you want to color code it, that's up to you. Once you are finished with that, and we watch the rest of that video, the next page is a page that you guys can do for homework. It's really easy. It won't take you long at all. It's based on the first few minutes of this video, and of course the next few minutes that you guys watch here at the end. Okay, so finish watching this and work on the homework, and we'll talk about it at a later point in time. All right, thanks.
The different groups Mendeleev had identified are a lot of the same groups that we study today. Starting at the left, we have the soft, shiny, extremely reactive alkali metals, so reactive, in fact, that they have to be stored in inert gases or oil to prevent them from reacting with the atmosphere. Alkali metals want nothing more than to dump off an electron and form a positive ion or cation, and they're always jonesing to hook up with a hottie from the other side of the table. So, of course, seeing as they're so reactive, you don't find hunks of them lying around in nature. Instead, chemists must extract them from compounds containing them. Next, you have the alkaline earth metals, reactive metals but not as reactive as the alkali metals, forming cations with 2 positive charges instead of just 1. Calcium, shown here, undergoes a very similar reaction to sodium and water, just a little more slowly, producing a little less heat. The middle body area of the table is made up of a nice solid rectangle of transition metals. These are the metals you think of as metals, with iron and nickel and gold and platinum. The majority of elements are metals. They're fairly unreactive, great conductors of heat, but more importantly for us, good conductors of electricity. They're malleable and can be bent and formed and hammered into sheets, and they're extremely important in chemistry, but overall surprisingly similar to each other. On the far right, just over from the noble gases, the halogens make up a set of extremely reactive gases that form negative ions or anions with 1 negative charge and love to react with the alkali and alkaline earth metals. The rectangle between the halogens and the transition metals contain a peculiar scattershot of metals, metalloids, gases, and nonmetals. These guys don't end up as ions unless you take extreme action and start shooting other ions at them, so generally a bit boring over here, though lots of interesting covalent organic chemistry. We'll get to that. Down below, in their own little island, are the lanthanides and actinides, metals that were largely undiscovered in Mendeleev's day because they're so similar that it's next to impossible to separate them from each other. And finally, on the far, far right, also undiscovered when Mendeleev built his chart, the completely unreactive noble gases.